Welcome back to The Explainer. Today, we are cracking the case on a major statistical mystery in episode 4 of Inside Time series. We've spent all our previous sessions looking at how historical data points influence the future. But today we are flipping the script entirely.
What if yesterday's forecasting mistakes could actually help us make better predictions tomorrow? Let's dive right into this provocative question. Because in data science, a forecasting error isn't actually a failure at all. It's a hidden signal just waiting to be decoded. Think about it. When a mathematical model gets something wrong, that discrepancy isn't just random noise. Often, it contains the exact missing information we need to correct our course.
So here's our roadmap for solving today's mystery. 1. When predictions go wrong. 2. Learning from mistakes. 3. The mathematics behind MA models. 4. Engineering applications. And 5. Combining memory and mistakes.
All right, let's jump right into section 1. When predictions go wrong. The hidden signal in forecasting errors.
Let's look at what happens when our autoregression models from our last episode inevitably make mistakes in the real world. Check out that 25-cup difference. That isn't just bad luck. It's a measurable residual, and it contains incredibly valuable information about what our model completely missed. Say our model looked at the trend, sales on previous sunny Mondays, and confidently predicted we'd sell 145 cups of coffee. But reality delivered only 120. That 25-cup error? That's our residual. And the real key insight of modern forecasting is realizing that if our model is systematically missing the mark, there is an actual pattern inside those errors just waiting to be mathematically modeled.
Moving right along to section 2. Learning from mistakes, extracting patterns from residuals.
Okay, before we go any further and actually solve this case, we have to clear up a massive misunderstanding in the data world. The moving average model is absolutely not the moving average smoothing technique we covered back in episode 2. I see people confuse this all the time. As you can see on the left, smoothing takes past actual values and averages them to paint a pretty laggy trend line on a chart. But the moving average model on the right, it doesn't look at past actual values at all, not even a little bit. It specifically looks at past errors, the exact difference between what we guessed and what actually happened, to actively predict and correct the future trajectory.
This flowchart brilliantly illustrates our new paradigm. It shows exactly how a mistake today literally becomes the fuel for a better prediction tomorrow. An actual event occurs, our previous baseline prediction misses it, we calculate the exact size and direction of that error, and then, instead of just throwing that error away, we feed it directly back into the engine for our next prediction. It is literally a feedback loop of continuous learning.
So, the crucial point to take away here is that while other models just assume tomorrow will be exactly like today, this model dynamically corrects its course based on its most recent failures. Autoregression says, hey, yesterday was high, so tomorrow will be high. But the moving average model, it says, yesterday I guessed way too high, so I need to pull tomorrow's forecast down to compensate. Let's get under the hood in section 3, the mathematics behind EMMA models, building the engine.
First, we have to define these things called random shocks, because they are the absolute fundamental building blocks of the moving average model. In the literature, you're going to see this represented by the Greek letter epsilon. A random shock is exactly what it sounds like, an unpredictable burst of variance. It's the sudden rainstorm that crushes your coffee sales, or a sudden viral tweet that completely spikes your website traffic. They are the true, unforeseeable surprises in our data series.
Now, instead of throwing a giant, terrifying equation at you, let's just unpack the blueprint of our engine. We've got a baseline mean, a random shocks, the weighted influence of those shocks, and our look-back window, which we call Q. So, if we have an MA1 model, that means Q is 1, and the model only remembers the single mistake it made yesterday. If it's an MA2 model, it remembers the mistakes from the last 2 time periods. Simple, right? The theta coefficient just tells the model how heavily it should weigh those specific past mistakes when calculating tomorrow's value. To really visualize this, if we look at an MA2 model on a correlogram, you can actually see the autocovariance abruptly truncate, just drop to exactly 0 at lag 3. This proves the model only has a finite memory of past errors. This is a massive hallmark of the moving average model. See, unlike an autoaggressive model, where the memory of a past event slowly decays over time, an MA model has a strict hard cutoff. If Q is 2, the model remembers lag 1 and lag 2, but by lag 3, that past stock is completely gone, forgotten. The correlation drops to absolute 0. And here is a super interesting detail. When we actually forecast into the unknown future, the expected value of future error terms is always assumed to be exactly 0. Why? Well, since we can't predict random shocks before they happen, right? We can use past shocks to correct our current trajectory for sure, but because true white noise is fundamentally unpredictable, our absolute best mathematical guess for a shock that hasn't happened yet has to be exactly 0.
All right, Section 4, Engineering Applications, Handling Sudden Shocks. Let's see this in the real world. Because it specifically focuses on errors, the MA model is literally the perfect tool for scenarios where a sudden anomaly disrupts the data for a day, but then the effect fades quickly. Think about a manufacturing plant. If a machine calibration is slightly off on a Tuesday, producing a batch of defective parts, well, that's a shock. An MA model uses that Tuesday error to instantly adjust expectations for Wednesday. But because it has that finite memory we just talked about, it won't let a one-off Tuesday glitch ruin the forecast for next month. It handles those transient, temporary shocks beautifully.
When we contrast the two side by side, it becomes crystal clear that they are designed to solve entirely different pieces of the time series puzzle. An AR model from episode 3 is kind of like a massive cargo ship. It captures momentum. If a stock price has been rising steadily for a week, the AR model captures that persistent inertia. But the MA model? It's like the shock absorbers on your car. It isn't looking at the long, smooth road, it's looking right at the sudden potholes, the transient shocks, and instantly adjusting the suspension to keep your ride smooth.
Which brings us to our final stop, Section 5, Combining Memory and Mistakes, the Ultimate Setup. So we know the AR model remembers what we observed, while the MA model remembers how badly we messed up. One leverages the actual data points from the past, while the other leverages the residuals, the unpredicted noise that the main trend totally missed. Neither tool is perfect entirely on its own.
This naturally leads us to probably the most exciting question in classical forecasting. What if we could combine both? Can we actually merge these two philosophies? Can we build a system that understands both the deep underlying momentum of a trend and also possesses the agility to instantly correct itself when sudden, unpredictable shocks hit the system? Well, yes, we can. By blending them together, we get ARMA, the autoregressive moving average. It's a model that leverages both the momentum of the past and the lessons of our mistakes to handle incredibly complex data. The ARMA model takes the P parameters from autoregression and the Q parameters from the moving average model, fusing them into a single unified equation. It's one of the most elegant and powerful forecasting models ever created. So I'll leave you with this final thought as we wrap up today's explainer. The past tells us what happened, but our mistakes tell us exactly what we missed. By understanding the moving average model today, you now have the final puzzle piece. But what actually happens when we fuse these two engines together to build the ultimate forecasting machine? Well, you'll have to join me for the next explainer to find out as we construct the ARMA model together.